So the matrix transforms from one set to the other, and they're going to call it on 64. They're going to call it a function or a mapping or a transformation, and then you're going from a mapping from the domain of one set into what they call a codomain in the other set, and then the range of values is in the transformation. So they're showing you a little example at the bottom, and the matrices is the transformation that transforms from the one set X over to whatever the other set is that you're transforming it into. And there's different types of transformations. When you were dealing in algebra, in college algebra, you had transformations. If you recall, you had a function, and then you would, depending upon where you added numbers, if you added it within the bracket, like if you had a function, if you put something like this, that transformed it 2 units to the left, and if you did it on the outside, that moved it up or down. So it's that kind of a transformation that you're doing. The matrices, though, is doing the transformation, and it's similar to the algebra transformations. And then the next section, you'll see that there is, when you took a function like this, you moved it about the x-axis, so then the y values change, and you'll see how the identity matrix will do that. And you can it's that similar idea that you had back then. And then they're giving you some, on page 66 at the bottom there, they're saying that the T is the transformation, and if you add in one set something like this, that if you do the transformation of those 2 vectors, it's the same as if you transform each vector by itself. So that's nice that transformation of a sum of vectors does that. And then when you do a constant, when you have a constant multiplied by your vectors, what you can do is this actually can be written this way. It's C times the transformation would be. This is U. So those are real nice properties that when you add a multiple of your vectors in one image, it multiplies the transformed vectors. All right, so we'll look at some problems. And number 2 there is saying A equals, and that's the transformation vector, and then it gives you the U vector, the V vector, and define the transformation of the R3 space into R3 space. So then it says the transformation is that AX. The A is doing the transformation on the values of x in the one space and converting it over to the other space. So when you do that, you just set your matrix up. And then you multiply it by the u. And then when you do that multiplication, it's the first row times the column. So you're multiplying the 0.5 times this value up here. And that's going to get you 0.5 here. Then you're multiplying, when you multiply this one times this 0.5 is multiplied by 0, so you get 0. And then this one times this, the 0.5 is times minus 4, so that's a minus 2. So that transformation then is taking the vector 1, 0, minus 4 into 0.5, 0, minus 2. And that's this A is the transformation vector matrix. So what you're getting is you're getting T of that U vector. And that T of U is this right over here. Now if you're going to do T of V, then you do the same process. It's your matrix, your transformation matrix. Times your vector in your R3 space. So that's ABC. So once again, it's just the transformation is 0.5A, 0.5B, and 0.5C. So you transformed this vector through this A matrix into that. So that this is just the new interpretation of what we've been doing up to this point. The next exercise says with T defined as T of x equals AX, find the vector x whose image under T is B. So we're here. Transformation vector. So what we're trying to find, so we're trying to find this. And that transformation has transformed it into 6. So what it's asking us to do is find what this value is. So what we've done in the past is we just did an augmented matrix and then solved it. So we just take that A matrix and then augment it with that matrix 6. minus 7 minus 9. And we solve it, and then what our solution is, if we have a solution, is going to be what x1, x is what we've transformed. So we just leave the first row alone. Second row, I'm going to leave that as is. And then the third row, I'm going to multiply the first one times 3, so it's 0. Negative 3, so it's, and that's a minus 9, so that's 4. Minus 6 is a minus 15. Minus 18 is minus 27. Was that 27 wrong? I'm multiplying negative 3 times the 6, 18. Is that that's a minus 18 and then a minus 9, or is that was I right or wrong? Okay. Okay, I'm working on the third row, the second column, third row. So I'm multiplying by minus 4. What's it 0? Multiplied by minus 4 is 16 is 1. Minus 4 is 28, and that's 1. Now what I want to do is I want to go back up. One minus 3. Let's see. I don't know why I put 6. I'm going to multiply this row, the third row, times a minus 2, so that makes this 0. Minus 2, that makes that 4. Third row times 4 makes that 0. 4 makes that 3. Second row times 3. Minus 9. Okay, so what we found is that the x1, x2, x3 is equal to minus 5, minus 3, 1. And the interpretation is that this A matrix is taking minus 5, minus 3, minus 1 vector in R3 and transforming it into an R3 space that gives us 6 minus 7 minus 9. So A is that, and that's what it is. That's what the interpretation would be. Okay, we got, let's look at 6. So once again, we got this matrix. 1, 2, Now, because there's 3 columns, although there's 4 rows, this is an X1, X2, X3. And it gives us, it transforms us into this 1, 9, 3, minus 6. So we're going from a R3 space to an R4 space, and the matrix transformation is that. And we want to know whether X1, X2, X3 is unique. So we once again will do the augmented matrix. Augment it with a 1, 9, minus 6. What I'm going to do is I'm going to move row 3 up to row 2. And work on row 3. I'm multiplying row 1 by minus 3. It's plus 6. It's 2. It's 2. 6. And row 1 by 3. 6 minus 1, 7. Did I do my multiplication and addition right? Now I got work on that row 3. I have to multiply by minus 2. Is that a 1? Is this a 1 or a 2? Is it 1? 0. Let's see. 0. 2. Did I do that last row right? I'm going to switch last row into the third row position. Divide that 1 by 1. Now, have I done my multiplication right? Am I right so far? I think so. Okay. So I'm going to work on first of all. So I'm still good because the that bottom row being all zeros is what it should be, because I only have x1, x2, x3. And make sure that I do my heading and subtract 1 minus 2. Now I'm taking negative times that row. So it's, and I'm going to do away with this one. So what I found is that my vector,
Top row on the far right corner, should that on the very bottom, you're good. But you got rid of that -2, right? So should you have to change the other one, the top two?
oh yeah, okay. I'm multiplying by this row. Thanks. Yeah, you're right. This one. I was thinking I was going times the bottom row. This is a 3, so I'm taking it times 2, right? 6, so that should be a 7. Thanks. Now, x1, x2, x3 has got to be 7, 3, 0. So that's telling us that 730, that this matrix right here is transforming 730 to that R4 vector. This vector 730 in R3 by that matrix is being transformed into R4, that matrix, that vector. And, you know, it's unique. This is unique and it exists. Now the next problem 8 says how many rows and columns must the matrix A have in order to define a mapping. So it's mapping R4 into R5. So you're taking R4, so you're taking X1, X2, X3, X4, a vector there, into a vector over here that's Y1, Y2, Y3, 4, 5, 5. And what you have to have is this thing has got to have the number of columns equal to this. So it's got to be 4 columns and 5 rows in order to map from 4 to 5. Because when you do your multiplication, you take each column times, it's a row here times this column. That's the way the multiplication. So you have to have 4 columns, and then you have to, in order to get a result that's 5, you got to have 5 rows. All right. That was all they were asking there. So 9 and 10, it says for all x in R4 that are mapped into the zero vector by the transformation x is ax for the given matrix A. Find all x. Okay. So 10. So what we're trying to do, so we're trying to find all the vectors, and it has to be x1, x2, x3, and x4. That's going to give me, and the columns are 4 columns, so 0, 0, 0, 0. So that's what we're looking for. So the way we'll do it is we'll augment the matrix with the zeros, find it, and then see what our result is. And we might have to have a parametric equation. So we want to augment it with the zeros. And the solution is going to give us our vector x1 through x4 there. So I'm going to move the third row to the second row. Enough trouble without trying to take too many shortcuts. So I'm going to eliminate the 1, so I multiply first row by minus 1, 0, minus 3, so it's minus 9 plus 3 is a minus 6, minus 2, minus 6, 0. And then multiply first row by plus 2, 0, 6, 9, 18, 9, 0. Man, was that is this a 9? I hope so. What? It was 9. 0, 1, 2, 3, 0. So now I'm multiplying the first row times a 1. 0, 0. This is 3 minus 4, 0. And the first row times the negative 3. Now you said that was 9, so 27 negative. That's -9. 6, that's a 3. So now I'm multiplying that third row by -3. Twelve, 8, no, 12, 9, isn't it? I sure don't like that thing's going to be a fraction. Is that row right? 3 minus 4, 0. I want to get that to be a 1. I'll divide this one by 1, 9, 5. But that don't look good. Is it right at that point? You think so? Are we good? What?
That's good.
Okay. All right, so 1, 3. Oh, I want to take that last row. I want to get rid of that one. Right. This is 0. 0, 1, 2, and multiply the last row by -3, so I'll get rid of that. And I'll get rid of this, right? I guess that I wasn't agonizing over 4 thirds and it went away anyway. I'm working on the third column. So essentially, just all of these numbers go away, right? 0, 1, 0, 0, 0, 1. That's a good deal. So it's saying the vector that satisfies that x1, x2, x3, x4 is this thing right here, right? And it's unique. There's only one of them. See, if we'd had something with parametric, then we would have been infinity of them. Okay. Well, it says let B equal that vector and let A be the matrix. In exercise 10, is B in the range of the linear transformation? Why or why not? So we're going to have to go through that same process again with this one. We've got to augment the matrix and see what we get. So we'll take that A matrix. And I'm going to go ahead and switch it because we switched these rows, right? First and second rows. I better be darn careful because we better switch that augmentation too. See that augmented value. This augmented thing was, the matrix was this. A -1, 3, -1, and 4. And what did I do? I switched row 3 with row 2. So I better put the augmentation with that switch in there. Right? Because if I'd augmented it, I'd have had that -1 and 3, and I switched them. Right? So I better be sure. That's what happens when you try and take a shortcut. You get yourself screwed up. Okay. Finally. Okay, 0, 6. Okay, is that one right? Or everyone going faster than I'm going? So I'm multiplying the second row by 3. 9, -1. Second row by 9, -9. That's 18, isn't it? So that's it. 27. So that's 18 minus. Second row by minus. Did I get that right? So that's going to have to be what? Negative 2/3, isn't it? It just doesn't seem right. Five-thirds. So multiply it by -1. And -2. What am I doing? I shouldn't even be doing that, should I? I should be going down. No, I should be eliminating the 18. That's what I should have done. So that's 6. 0. 6. This is 17. Now, at that point, that can't be true, right? This thing here says 0 is equal to 17. So that can't be true. So it's an inconsistent set of equations. Okay. And so in answer, what was this? Questions asking 12. Let B be that. Let A be the matrix in 10. Is B in the range of the linear transformation? And it's not in the range because it's inconsistent. There's the transformation. We can't get that value that will transform into that B value. So there's no vector in X that will transpose into the B vector. The next group says use the rectangular coordinate system to plot the U and V and their images under the given transformation T. So our transformation vector and it transforms it into 5, 2. So it's going to be we can augment it. Then we'll find the x1 and x2. You have to double this to make it 1. So that's saying that the x1, x2 is 10, 4. And so that's just doubling it, or halving it. There's that. So this vector is x is 10. If we use this as 10 and 4. And it transposes it into 5 and 2. So you see it's just half. So that's what the vectors do, or that transformation is doing. It's just halving the vector. Okay, 16. And, oh, I didn't do that other one. Well, it's just going to half that other vector. 16. 2. So it's taking the vector 2, 5, and the transformation is transforming it into vector 5, 2. So our vector x is 2 and y is 5. It's right up there in that, up in here. and transforming it into 5. So it's taking that vector and in that 2x2 space, it's transforming it into that vector. And it'll do the same thing. It'll just interchange on the B. It'll just flip that one over. Okay, 18. Okay, it says the figure shows vectors u, v, and w along with images t of u, t of v under the action of linear transformation, transforming from R2 to R2. Copy the figure carefully and draw the image t, w as accurately as possible. So, and then put some vector out here and a vector there and a vector back place here. I'm going to call this one U, and this one W, this one B. Don't like it. Now, what we'd do is we draw a line parallel to B here, and a line parallel to O. I might not have drawn this quite, but if I'd have drawn it correctly, this distance should be 2 times B. And so this vector W is equal to U plus 2V. So then if we go to our and that new one, transform. That's going to be TV. And so okay. So we draw a line parallel to V through U up here on top. And then we draw a line. I'll draw a line from V parallel to U. Let's see. Through V parallel to U. Now we said that the V, it has to be twice as far out. I didn't leave myself enough room. This should have been, I should have been able to go out here. And that, this is supposed to be, because should translate into 2 PV. And then I have to think what I do. So I gotta go from screw that thing out. It's gotta go here. Okay, that is going to be the transposition of the function. Okay. I hope you understood what I tried to do. That last one, it's saying that x equal x1, x2, v1 equals 2, 5, v2 equals 7, 3, and let the transformation be 2 to 2 be a linear transformation that maps x into x1, v1, x2, v2. Find a matrix A such that the transformation is ax. So this one, 20. It's just x1, v1, So what, all you do is just put that V1 minus 2 and so the matrix is just 2, 5, 7, 3 times the x1, x2. And this is then the matrix. Minus 2, 7, 5, 3. That does the transformation. Okay. I'm quitting. Any questions?